All right, let's get started. So welcome everyone. Welcome to our talk. Happy to see you all. I hope you're excited as we are. Today we will talk mostly about the topic of software-defined vehicle and how HMI comes into that. So the automotive industry is going through quite a bit of transformation. One of them is being that the next generation of cars will probably be mostly software-defined. They also try to reduce the development time from 5 years to 2.5 years. So there's quite some challenges in there. Are you all familiar with software-defined vehicle? That's good because I usually like to show this image as a comparison. So I describe software-defined vehicle as a smartphone on wheels. It's the same concept, so you go to the store, you buy your phone, and it's going to be the same hardware from the first day until the day that you hopefully recycle it, unless you have an unlucky accident, of course. But the power is not in the hardware, that remains the same. The power is in the software, because you open up the box and you start installing applications. That expands the functionality and the usefulness of your phone. Also, sometimes you get updates on the operating system that unlocks powers like making better pictures through AI, for example. So the same is happening to vehicles as well. So the vehicle hardware remains the same throughout its life cycle, but it's all about the software. So there's quite some different aspects of the software-defined vehicles. I think we can do like an event like this, all describing those different topics. But today we want to focus on a few of them. And that's like the software first principle. So it's all about software development. And the way that we as users interact with the software is through screens. So that's where the HMI topic comes into place. So today we want to present two projects that we expect will help you define and help you develop your HMIs in a better way. Before that, let's be polite and introduce ourselves. So if you want to still escape, you still have the opportunity to do so at the moment. I'm Karel. I'm an industry process consultant at 3DExcite. So that means I help clients define what tools and processes they can use to achieve their business goals. And with me, I have my lovely colleague Timon, who is a senior solutions architect. But I usually call him one of the mad scientists who create really interesting and cool new tools and processes.
Let's see.
We are representing our company, 3DExcite, at the moment. So we are part of the Dassault System ecosystem and series of brands. And we help our manufacturing clients to develop their products and bring them to the market. So our expertise at 3DExcite is around the visualizations. So our expertise and core business is transforming the engineering virtual twin into what we call a commercial virtual twin. That means we take the engineering data, we optimize it, we enrich it with extra data, strip out IP, and we create a virtual twin that can be used for visualization or experience purposes. The way they do that is manifold. On one hand, we have our services organization who runs through the pipeline and then creates experiences like images, videos, applications, but we also develop the software to do that. So we have our legacy software DeltaGen, which is a data prep and rendering tool. We also build solutions on render on demand, so Unreal powered. And we also develop for the 3D experience platform as Dassault. So we have applications that automate the data processing and optimizing, as well as visualizing and authoring experiences. But I see some of you look at us and see that you recognize us. And that might be true because we were at Unreal Prague last year. And we did talk about our solutions, which are render on demand based, so Unreal powered. And those come in two flavors at the moment. So we have 3DExcite Show, which is an API access to the virtual twin on the cloud powered by Unreal. So you can get assets live rendered into your applications and websites. And we also have 3DExcite Show, which is more of a user interface kind of thing. So it implements the same model in the cloud, but you have a nice interface, so you can configure your cameras, lighting, and things like that. We do have some improvements, and I will hand over to Timon to quickly highlight that.
Sure, thanks. Yeah, so first and foremost, last time I think we just showed a screenshot, but that's basically what we give developers outside of our organization and also inside as a tool to explore the set of APIs that we create with Show. And in there, what you can do is like you can all the features that we have in the API you can access there. So any variants that are within their variant families, you can switch them. You can change the environments. There are cameras based on environments or generic cameras, and you can just start playing with the tools that we have. And just for Unreal Fest, we added a new button, which you will see in a bit. But also it gives you like all the metadata about all the individual things that we have in there. So aperture, field of view, and these are not baked into Unreal, but we inject all these settings into Unreal at runtime. So you can have a bazillion cameras if you like, because it's just a database field. And what we have here is a new tool that has a catchy name called Create PAK. Oh, wait. And what that does is it triggers a process that might come in handy later in the talk. But we're not really stopping there, but we're always trying to improve on the data that we have. So we brought you a little video that we made.
Every day is different. Every person is unique, and everyone has their own path. But what if your car wasn't just a vehicle, but a companion that adapts to you, to your life, to your stories? This is the power of software-defined vehicles. Cars that evolve with you, respond to your needs, and make every journey personal. Now, imagine reaching your customers the same way. Without a video engine, you can create automated dynamic videos that adapt as flexibly as your next generation vehicle platform. Videos are created and configured based on interests, and even the storyline adapts automatically. Videos on demand, powered by 3D Excite Show.
So that's quite interesting, the virtual twin in the cloud being rendered into video content using Unreal. So that's definitely something that can be useful to a lot of you. But today we are talking about two different topics about HMI. So first of all, the project that we would like to present is how do you optimize a model to be used in an HMI system, which needs to be super lightweight. A separate topic that we want to discuss is now that you have a lightweight object, like lightweight product in your HMI, how can you better design and validate your HMI system while you're developing? So that is what we are going to highlight today. First of all, it's about optimizing the HMI model. So we see that in HMI world, there's quite a shift from 2D old school configurable HMI systems to like powerful 3D engines running inside of the HMI system like Unreal. And that needs a super lightweight optimized model. And we are going to show exactly that, how we do that. We don't want to start a completely new process for that. We want to integrate that in already existing processes. So our clients are mostly automotive and aerospace related. So they do already have their data in CATIA V5, CATIA on the 3D Experience platform. So we start there with that base. And we use on-cloud processes, our tools, to optimize the data there as a first step. So then we enrich the data there. So we have like the commercial virtual twin ready to ingest into other 3D applications like Unreal. And then Unreal unlocks functionalities in our solutions like 3D Excite Show, 3D Excite Create, but also what we call access to enable you to have an API to download or use the actual optimized streamlined models. For example, HMI purposes. And that's what's exactly what Timo is going to present to you, how we see that and how we are going to do that.
Yeah, so access. We've already shown like how we are bridging the gap between engineering data and then visualization ready data. And that process didn't fundamentally change since we last time talked about it. It's a living process that ever evolves, and we're putting new features in there all the time. While show and create are more aimed at the final pixel that we want to show, being it a 2D image or a video, access kind of goes away from there, and what we are trying to do is shift the pixel creation more to the edge or onto the device that you might have. In today's case, an HMI. And there's nothing much you need to do. It's just another API in the suite of APIs that we have. So all current models that we are shipping with show and create today can and will most likely benefit from the optimizations we're doing through access. And there are a few bits and pieces that kind of make it easier in the future to get to a more optimized and real-time capable on-device model. So for that, we would like to show something that we're currently actively working on. So it's not set in stone. These are like thoughts that we had about HMI systems and data optimization for these. So if there's anything you like to address or you have concerns on, please talk to us. We would like to just get in touch early and get the things as good as you might need them, right? So wouldn't it be great to have more the right-hand side in the HMI than the left-hand side? And part of the equation is the time it needs to build up a model that is real-time capable on a teeny tiny device. So what we're trying to do is remove that step and let you access, pun intended, your twin within the HMI without maintaining just another model and reduce data sourcing times and stuff like that. And in fact, Unreal is a great tool. So if you've looked at the Lotus outside that runs Unreal, looks super cool and it has all the great features. So just to get a story, let's assume you have a great configurator with show and you're doing some like offline images with create, and you have all the tools, and you can just use the same data sets to create a 100% configuration for the HMI for that. And it's just one API request away. Actually, it's two, one to produce it and then one to fetch it, but it doesn't really matter. But before we can request these, we might need to do some data cleanup. And that's normally like a error-prone, super manual process. And we're trying to find ways to bring these complex all-use case data sets that we have for show and create into shape, form, and size that allows rendering on these small, low-spec devices. Yeah, and to be honest, it's a little miracle what you can put into these devices nowadays, right? So it's as big as your phone, and it can render like 30 FPS, and we'll see it in a bit. And once you start with that process, it kind of feels like, yeah, that's quite trivial. We just throw away stuff, we optimize stuff, we scale down textures. But the more you think about it, the more complex it gets, as always with these trivial things. And what we are introducing is a way to tell the Access API what is actually needed for an HMI. So you might not want to have all the geometry in there, or you want to have per geometry family reduction settings, so something can be more compressed and others don't. And we are allowing that through tags. So these tags are fetched from the upstream twin in the platform. And in Unreal currently looks a little bit like the right-hand side. So they just have a value there and you can put stuff in there. I heard that there might be something around the corner with metadata-based workflows, but we'll see. But back to what we came for is the virtual twin on the HMI. Excuse me. And we now have like all the data enrichment, and we know what we want to throw away. So let's just look at how this looks like, and that's about as good as it gets for today. First and foremost, the 150% model is already optimized. So it already is like a super optimized version of the engineering twin. And we have teams working on that. But to make it run on an HMI, there's quite a lot you need to do, actually. So these models that we have are like made for 8K super close-up detailed shots of something, but you might not want to need like that amount of detail in an HMI. And additionally, it holds data that is relevant to all the downstream use cases, so we just gonna get rid of them for that. And it's gonna take a little while, but I'm just gonna show you what's done in there. So I asked one of the developers to like give me a brief overview of what is actually happening in these progress bars. And if you want to replicate that, you can just take a picture of the process. There's quite a lot going on in there. And that's actually really important because what we want to get to is gigabytes of data down to hundreds of megabytes. And the result of that process is a PAK file. And you might ask, what is a PAK file? Essentially, it's how Unreal stores your cooked data, or it's a way to store cooked data and then load it at runtime. So for now, let's think it's just like a zip file, basically. And it has all the data that is needed to show what you want to show in the running application. And there are a couple of ways to make sure that just the data that you actually need is in the PAK file. So for instance, have a look at primary asset labels, pretty cool tool. And then once you have these PAK files, you can mount them at runtime. And that's important. It's only working at runtime, and it's only working on actual built applications. So no plain editor. It's a runtime feature. And then once you have these PAK files, you can just load them. So now we kind of know what's happening on the Unreal side. So let's take another look at how these APIs for access work. And it's not a one-size-fits-all API. It's a set of APIs that should allow our customers to define workflows that fit their needs. So we're not trying to dictate anything. It's more a, here you go, use what you need. And it can follow standards. It doesn't necessarily have to. Standards are great. We love them. But it could be like bespoke to what you would need. And then you have this little guy in his car. He has a great hat. And he's trying to get the file in the car into his HMI. So he asks access and kind of like tells him who he is. For instance, with a VIN. So that's the ideal world. So the car says, hey, I'm that car. And then we or the customer has a process to map the VIN to the actual configuration of the car. So for instance, you have your VIN, and then it says that's a red car, and it has 4 wheels, obviously. And And in that process, so once we have the options, we have a couple of middlewares that sit in between, where we can do like data cleanup, sanitization, and whatnot. When I say we are running these through systems, normally that's a cloud-based system because that's how we started. But we've actively been pushing parts of that process and other processes into edge devices. So the system could be an edge compute device on your production floor, and it has the data, and you don't need to fetch it from AWS or someone else. So this is a beginner's talk. What is a VIN? Basically, that's a VIN. It's a serial number. It kind of identifies the car. But storing a file for each VIN might not be really necessary, because in the end, let's assume you have a car that comes in 2 colors, and you sell 1 million of those. You wouldn't need 1 million HMI files, but rather 2 for the 2 colors, and then you map the input to the output. And it kind of like makes the process a little bit easier. But to be honest, real-life data sets are way, way more complicated. So it's still a lot of data. So now that we have the options from the VIN, we just a couple of months ago introduced a little tool into our APIs, where the middleware, which is a process that sits in between the request and the response. So we have ways to hook into that request and rewrite it at request time. So for instance, on the right-hand side, it looks like JavaScript because it is. So we found that JavaScript is like pretty accessible to everyone, and it's kind of readable. So we have a little JavaScript engine that runs as part of our backend APIs. It's a very limited subset of JavaScript, so you cannot do like HTTP stuff. So it's a closed garden, but it allows you to do data rewriting if needed. And it can run at multiple stages within the pipeline. So you might remember the sandbox that I showed in the beginning and the create PAK file. We actually tried bringing a live demo, so we do have an Android device. Unfortunately, Wi-Fi stuff this morning, so we have a pre-recording of that, but we got a nice template from Epic called the Nova HMI, and that's it. Well, that will be it in a bit. So at the start, we authenticate and we just say who we are. In this case, we are the yellow car, as we've seen earlier. And then the data gets fetched from the cloud. It's around like 200-ish megabytes for that full car. And then we added just a few mock-ups, like you could do HVAC, which is packaged separately. So you could have a process within your HMI where you say, hey, we have the car, great, but we also have an HVAC that we want to like update, or if you have a new feature, you could add that. That's also a great animation which comes with the Nova HMI, and if you want to get it, it's probably talking to Doug. So it's a great starter project, and we just changed the UI a bit so it kind of looks different. Yeah, and then you can like have your HMI do stuff. So all the animations that are baked into the upstream 150% twin. If you remember the initial slide of the two outliners. So we keep those animations and we can play them and hook them into your sensors as needed. And I was a bit too quick because we were waiting on showing how fast it runs. So this runs on a Samsung tablet something. And as you can see, we render at 2.5K, so it's 2560 times 1600, so quite a few pixels, and we're running around 30-ish to, depending on the compression of the model. So this is like a high quality model, but we can compress it further, and we've seen numbers as high as 60-ish FPS, because after that the device doesn't produce more pixels. So it doesn't come for free. There are a couple of challenges. In fact, there are quite a lot of challenges if you want to put something that runs great on commodity hardware and super expensive GPUs into a small little device the size of your thumb. And it's a bit crazy. So let's just quickly talk a little bit about the challenges. And these are the challenges that we found. And this is mostly what makes up a computer device, so everything. And you, as Kara said in the beginning, you cannot just change the hardware. It's in the vehicle for the lifetime of the vehicle. So you can also not just put a new GPU in there if there's a new update or whatnot. So let's look at just a few numbers just to get an understanding of where we are. So on the left-hand side is a benchmark of the Android chip, and on the right-hand side is a typical artist workstation that we have on our production floor. There's quite a difference, and that's just the CPU. It gets more impressive if you look at the GPU, which is the interesting bit if you want to do 3D rendering. So it's quite a difference if you compare it to, for instance, NVIDIA RTX 6000 Ada, forgot the name. And then the same applies for file size. So the unbaked 150% model might be in the gigabytes, but ultimately we want to ship it within 200 to 300 megabytes probably, or even lower, depending on the actual needs. Yep, and it's an ongoing process, to be honest. So it's quite complicated, more complicated than I thought in the beginning. But we're actively working on it because it enables stuff that Karel does.
Thank you. So we see that a process is possible to deliver super small, optimized, streamlined models for the HMI purposes. But another question that we had is how can we help in developing an HMI system, like the design and the validation of that in its context? Because we were talking about software-defined vehicles, and we are used to talking about virtual twin as, yeah, it's geometry, there's materials, there's some configuration logic, and that's it. Usually that's our basic view of what a virtual twin is. But when we talk about software-defined vehicles, we talk about software, we talk about systems engineering, we talk about actual behaviors of the vehicle that also needs to be included in what we see as an holistic virtual twin. So the interesting part happens when you start linking those things. So you try and use that behavioral functional information and you link that to the other parts of your virtual twin. So as a concept, I embarked on a small project, an experiment that tries to bridge the gaps between different disciplines that you encounter when you develop a software-defined vehicle. So on the one side, we have systems modeling, which I will explain to you. Then we have the HMI system, like the interface running in the 3D car, which runs in Unreal. We want to couple that and move it back to the actual engineering data to validate if how it works, is the ergonomics okay, things like that. And we don't want to do that in a flat 2D world, but we also want to do that in an immersive headset. So that's the scope, and we wanted to do that with a very limited scope, being an EV charging cycle. So now we come to the interesting thing. Systems engineering, that's something that none of you are probably familiar with. And the good news is I'm gonna transform you today to systems engineers. So to prepare for that, it needs like a mental shift. So you're used to having nice Unreal UI elements. So you see it, like nice blueprints and things, forget those. We're going back to the 2000 years. So imagine Windows XP, that kind of GUI style, we are venturing in that world. So when we're starting to design a system, we use an approach called model-based systems engineering. So that's a way to better capture and analyze things like requirements, design, and behaviors of a system. This is done using a modeling language. In this case, it's XML. It's not like a normal programming language. It's more like a methodology, a framework that works with diagrams. And there's 9 diagrams. Luckily for you, I'm not gonna speak about all 9 diagrams, but we are limiting ourselves to 2. Beautiful. So we have our base diagram, which is a block diagram. Here we design the actual system, like the different components of a system. I wanted to show a charging system, so we don't need a lot. We don't need tires, we don't need an AVAC system. We just need a representation, a box that says it's a car, and the car consists of 2 parts, like a battery, charging system, and then there's external systems. There's a user and there's a charger. And the user can plug in the charger into the car and then it can start working. But we still need to model all that. So that's the basic, that's the system. Now we need to talk about how does the system look like, not from a visual perspective, but what are its properties. So we add properties. We are adding values like the battery, how much capacity is it? The charger itself, how much power does it put into the car? So those things we add as well. So now our model is a bit more complete. So we have more complexity. Next step is we can add what is called constraints. It's like the computational values. For example, if you want to calculate how long of how many kilometers you can drive with the current charge, you just take the variables that were already existing on our blocks and you calculate them. But now it's a static thing, so it's boring, you can't do anything with it, but you can start communicating with the rest of the teams or different departments, like these are the basic components of the system, this is how it will work, and this team will work on this part, and the other team will work on the other part, but the property names are defined. So if someone works on the capacity of a battery, we know it's called capacity, interchangeable between departments. Interesting thing happens when we start with the next kind of diagram, which is called an activity diagram. And I see you looking at it and you say like, yeah, that looks a lot like a blueprint, and you would be more or less right. You have a starting point, an end point, and between those you have a flow of lines, and in there's actions. They're called actions here. And sometimes you have these signs like, do I have a pointer here? I don't know. Which is called decision nodes, and that's like a branch node in Blueprint. So is it this or that? And defining on that, you take a different flow through your graph. And that's how you basically describe the behavior of a system. So this is a charging cycle. So the user plugs it in, it starts charging until a certain level, usually like the 80%, and then it stops. But I added like the MQTT logo because I don't want it to be a siloed dumb system. I want to have communication outside of the system model. So some of the blocks you can see, some of the actions, take the variables of the model and take it out of the systems world and put it out in the general world where you can hook it up to Unreal and other use cases. And it also listens to commands. For example, if a user says like, I want to charge to 100% because I want to make a long trip, he must be able to do that, and the system needs to know and recalculate everything. So all the logic is put here. So when we have that, we have done that all in software like CATIA, Magic, Systems of Systems Architect. And then it runs like this. So you have set up a simulation, you press play, you see it instantiated all the blocks, and it starts going through the entire flow. What you don't see here on the screen is, in between all the different iterations, it sends out all the variable information outside of that world. So congratulations, you're all basic systems engineers now. And to reward you, we are moving back to a world that you're quite familiar with, and that's the world of Unreal. Because now the next component in this project is building an HMI system, or an interface for an HMI system. So we take, first of all, the car, which ideally comes out of the workflow that Timon described before. We add geometry, lighting, we add some Niagara particles, because that's always a fun thing to do. And then next thing, we add logic. So in this case, it's just an MQTT connection that we create, because we want to capture the variables from the systems engineering model, insert that into Unreal, and we want to do a backwards data stream as well. So if we change something like the slider that sets the charging level in Unreal, we want to send that to the system engineering model as well. So that's how we do that. Next, we of course create the UI itself. You can see I'm not a good UI artist, so don't hire me for those purposes. And you have some logic around that. The logic is just updating and formatting of the data. So there's no actual logic in the charging cycle world that's in Unreal. It's all in the model systems engineering world, but it does the formatting and updating. So when you run both systems at the same time, you can see at the bottom corner the actual simulation is running in the CATIA software, sending all the data through MQTT to an MQTT broker. And we have Unreal loading those variables, populating them, changing it in the interface. You have also a slider to change its charging level. You have a button stop charging, and that interacts again with the systems model. So now we have two branches of the software-defined vehicle world working in tandem. So you can see what's happening in a more abstract engineering world. And you might, in your use cases, stop there. Might be enough to see like, all right, my system is reacting in that way. I see it populated, it works as intended, and that's fine. But I wanted to go a step further, and I wanted to see how the interface would look like and how you would interact with it in the context of having engineering data in there. So for there, we move back to the 3D Experience platform in an application called Creative Experience, which loads in CATIA data, so it's the engineering data itself, all NURBS. Also connected to everything else, so if an engineer updates it, it automatically updates in Creative Experience. And we have a lovely component called a 3D Web View. And that's just a browser window into the world. And the nice thing about Unreal in the latest versions is you have pixel streaming right in the engine. So you don't need to compile anything. You can just press pixel stream the editor to this address. And here in this experience, you say like, load this address. And now you see the Unreal rendered engine, HMI engine, just running here in Creative Experience, and you can interact with it. So the slider still works, the stop button still works. That's quite powerful. I wanted to push it like one step further and see how that would work in an immersive world. So as you might know, in June, Apple and Dassault System ventured on a partnership. It was basically about collaborating on delivering platform experiences on the device. So things like design use cases, training, and guided work use cases. So things like that was the primary focus. So I worked on a few demos with the AVP. So I thought, let's try and put everything in there as well. So it works with a custom native application called 3D Live, which runs on the AVP. And from there, you load in the experience that I created and showed before in Creative Experience. So you put the headset on, you select the experience, it downloads it, it loads the experience, it starts it, and you have like your car, your engineering data in the headset. The nice thing is, so this is just like the external part, but we exported everything. So the actual HMI that's currently being rendered in Unreal, driven by the engineering model, is running live in the AVP. So you can see as the world's worst designer, I made a lot of mistakes, and that you can validate now. So I have a tablet-sized screen, not the best place to put it behind the screen. Also, my user interface is blocking most of the time the stop charging button and the slider. Really bad UI design, but that's the entire purpose. So I can now validate whether what I do in HMI, in engineering, is working or not, and make adjustments. And in this case, I can, on the fly in the editor in Unreal, change the UI. And since it's just pixel streaming, it updates immediately. So that's quite a powerful thing. So that's my keynote after this experiment. And that's to encourage you all to take more of an holistic view on the concept of a virtual twin. So don't limit yourself to its geometry and variants like configuration logic and things like materials, but also keep in mind that there's a powerful component being the behavior information. And you don't need to do the full-fledged thing like I said. You can start with Figma in an engineering model. You can start implementing in a next step Unreal and the engineering component and do like a software in the loop kind of story. You can connect things like on the left side, you see Scanner, which is also CATIA software. Funnily, it's driven by Unreal itself. I think they're still stuck in the 4 dot something releases, but it simulates traffic and sensors. So if, for example, you want to open a door and there's like a cyclist coming on, it detects it, it simulates it. But that's also something you can plug in into the entire ecosystem and see what that would mean in context of your HMI system. And then you step forward in your development process, you add hardware components until you reach at a certain point your final product. And that's quite interesting. And I think, well, I believe, and we as a company believe, that this is a way that can really speed up your development workflow, both from an HMI perspective as well as the entire software-defined vehicle story. So it's experimental, it's just putting things together right now, but it opens the door to a lot of interesting use cases. So if you're interested in working together on this, or if you have ideas, we can put something together and we can talk about that. I think all the time is up right now, so I don't think we have time for any questions, but we are, of course, available outside and the rest of the day for any questions, demos, and if not, we can always mail us or find us on LinkedIn. Thank you very much.